Hello, Deep Learning Training Pipelines on the Cloud. In this video, Building Deep Learning Training Pipelines, we will look into challenges of building Deep Learning Training Pipelines and how AWS Batch can be used to tackle these challenges. Let's start by defining parts of a deep learning pipeline. Training pipeline usually consists of the following steps: downloading training data or mounting it to the execution container, importing the pre-trained model and setting up model architecture, model training itself, which happens based on input hyperparameters and configuration, producing metrics for the training and generating output for the training, choosing the best model based on metrics, testing it on the dataset, and exporting the model with metadata. Let's take a look at the first step. There are usually multiple options when preparing data for the training. One option is to download the dataset from the file storage. On one hand, it provides us a way to keep track of the dataset, which participates in training. But on the other hand, we have to spend some time in the beginning to download the whole dataset, which could be hard in case the dataset is extremely large. Alternatively, we can keep the dataset as part of the container image. This way provides very fast access to data during training, but at the same time makes it harder to reuse the same container image for a different dataset. Next, we can mount the data volume to the training machine or stream data from the file storage. The main difference here is that we never store the whole dataset locally and download images entirely on demand. AWS SageMaker provides a convenient way to stream data from S3. Finally, we can only download images from the outside source when they are needed for training. It helps to reduce local storage constraints, but at the same time may significantly increase training time. Once data is prepared, we usually need to download a pre-trained model, which will be used for constructing our model. You can either download it from one of the public storages or keep it as part of your container image. Alternatively, you can keep the model as part of your private data storage. One of the main challenges of training a neural network is reproducibility, meaning that we want to be able to reproduce training for every model which we use in production. To achieve that, usually whole configuration and parameters are kept as model metadata, which is saved with the model. It is mainly used for the cases when you need to optimize the model based on hyperparameters, or trace the training process in case of degraded model performance. Model metadata also helps to make sure that training during experiments and in production perform in the same way. To optimize model based on hyperparameters, we need to generate and handle multiple sets of hyperparameters. One additional thing you would want to keep it as part of the configuration is the set of versions for every part of the system which participated in the training, such as the version of the dataset, the version of the code used for data preprocessing, the version of the code used for training. To reproduce the model training successfully, you may also need to keep random seed values that were used during the training. Once the model is trained, and the best model is chosen based on the metrics, we need to validate and test the model. Model testing is crucial for production workflows, as it enables us to make sure that we get a predictable performance on real data and check for model degradation. To check for model degradation, the usual way is to get model performance on the dataset, which didn't participate in training in any way. Keep in mind that in this case, we don't want to optimize model's metrics based on the dataset, like accuracy or F-score, but rather that we get performance and check that it performs better than some baseline which we set. An additional way to check for model degradation is to compare its performance with the current production model. This comparison allows us to catch sudden differences in model performance. Also, it could be useful to test the model on specific edge cases, like black image, image from completely different dataset, or empty image. To make sure that the model can work in a production environment, the best way is to check model memory consumption and model inference timings. Additionally, we can verify that it is compatible with all versions of the environment, which are used for inference in production. It could be useful for the cases where the model is primarily used on mobile devices or edge devices. After the model is trained and tested, we need to upload the model to the data storage. There are certain things which we need to keep in mind. First, you have to set up the storage for both model itself and metadata, which enables you to keep track of which data and hyperparameters were used for training. Second, is that there are different ways how you can export the model based on your case. Sometimes you may need to export the whole model checkpoint, so you could retrain the model later. Alternatively, you can export only weights for cases where you always retrain model from scratch. Finally, you may need to run a separate conversion program, which would convert your model in a format most suitable for a specific device, for example phone or edge device. For example, in our project later in the course, we will use TF-Lite conversion so that we will be able to use a fast and lightweight TF-Lite library for running the inference. There are multiple challenges when implementing deep learning training pipeline. First is the cost of training, as GPU machines are usually pretty expensive. Second is pipeline reliability, as you may want to resume training from a specific checkpoint in case GPU machine fails in the middle of the training. Alternatively, you may want to restart the training from scratch. Also, you may need to run multiple training sessions with different sets of hyperparameters in parallel, so that you can choose the best model afterwards. Also, there are special cases where it may be harder than usual to organize a deep learning pipeline. First is human in the loop, meaning that after each training iteration, we need to show the results to the person and then retrain the model based on his or her feedback. The second case is using external infrastructure for training, where we want to integrate GPU machines outside of our infrastructure to save on the cost of training. Let's take a look at how AWS Batch, AWS Step Functions, and AWS Lambda allow us to handle these challenges. AWS Batch allows us to use on-demand spot GPU instances for training, which helps to decrease the cost of training. AWS Step Functions provide a way to run multiple training jobs with a different set of hyperparameters in parallel and have custom logic for error handling. It could be used for both of the special cases mentioned before. In the case of human in the loop, step functions can wait for the event and then rerun the training. In the case of external infrastructure, step functions can pass task token to external infrastructure and wait for a task to complete. AWS Lambda provides extremely scalable processing with focus on short tasks that don't consume a lot of RAM, CPU, or hard disk. Let's look at specific patterns that could be organized using AWS Step Functions, AWS Lambda, and AWS Batch. First one is separating training and testing within the pipeline. In this case, training is done on AWS Batch, and inference testing is done on AWS Lambda. The idea here is that you can test that your model operates correctly with framework which you use in production, and check its performance on a separate dataset, as well as RAM consumption and speed. Second one is the usage of external infrastructure. In this case, instead of using AWS Batch for training, we will create an async task which will be requested by an external server. Server will receive the task and then use the data from it to access data and parameters from S3. After the training, the server will upload model artifacts and other data to S3 and will make a completion request to step functions. After that, AWS Step Function and AWS Lambda will handle model checking, completion, and publishing. The main advantage here is that it enables to keep external infrastructure stateless and to manage retry logic and monitoring on AWS side. Final pattern is human-in-the-loop architecture. In this case, we run training, then we run inference on a separate dataset, and then we get into the async state, similar to the previous case. The difference here is that we wait for the operator to give feedback about predictions of the model and possibly relabel the data. In case the feedback is significant, the model could be retrained and the user would see the updated results. Let's look in more detail on how AWS SageMaker and AWS Batch are different for GPU training and what are the cases where they can be used. Basically, we can see that while AWS Batch is cheaper than AWS SageMaker and takes less time to start, it doesn't have a number of features that could be useful for training, so you would have to implement them by yourself in the configuration and training code. The upside is that both AWS Batch and AWS SageMaker can be integrated with AWS Step Functions. Thank you for listening. This concludes the end of this video.